This lecture is about analyzing RC circuits using Laplace transforms. Let's start by analyzing an RC circuit the way we might normally do it before we use Laplace transforms. I'm going to start by drawing the RC circuit. The input voltage to the circuit will be called U, and the output voltage will be called Y. We'll say something in the op-amp lecture about having voltages that just sort of sit out in space without any clear source where they're coming from. For now, let's take it as a given that U is a voltage that's totally independent of whatever circuit we build here, and that no current flows through this terminal in the direction of Y. Okay, so we know the fundamental equation for a capacitor is that the voltage on the capacitor Y is equal to 1 over C times the charge on the capacitor. We also know that if these two voltages are different, then current will flow through the resistor, current I, and I will be equal to U minus Y over R. Now, if we take the derivative of the capacitor voltage, we can write dy dt is 1 over C times Q dot, and Q dot is, of course, just the current, so that's U minus Y over RC. And so what we have, we end up with the differential equation RC dy dt plus Y equals U, which we recognize as a first order filter, also usually called a low pass filter. If we did this with Laplace variables, we know we could take the Laplace transform of this and arrive at the transfer function y over u equals 1 over RCS plus 1. Now let's treat the capacitor as an equivalent resistor using Laplace variables. We'll start by drawing the capacitor again. And we'll say the voltage across the capacitor is V. The charge on the capacitor is Q. Current flowing through the capacitor is I. And of course the capacitor has value C. Now we know the fundamental equation for a capacitor is V is 1 over C times Q. And if we take the derivative of this equation, we get V dot is 1 over C Q dot, which is 1 over C times I. If we now apply the Laplace variable to this equation, we get SV equals 1 over C times I, or V equals 1 over CS times I. And now we see we have the equation that looks familiar to us from analyzing resistors, which is V is equal to R times I. And we can use this equation for a capacitor if we just call this R equivalent, R sub E, and identify it with 1 over CS. So now whenever we see a capacitor in a circuit, we just replace the capacitor. A capacitor becomes a resistor. This is C, and this is a resistor with resistance 1 over CS. We'll usually only draw the capacitor. We won't usually draw it this way. We'll still draw it as a capacitor, and we'll label it as 1 over CS to remind ourselves that we're using Laplace transforms to represent capacitors. Let's try it with our RC circuit. So now we have the RC circuit here like this. U is the input, Y is the output. And we've labeled this as 1 over CS. Now we know if these are just resistors, this is just a voltage divider. So the ratio of the output voltage to the input voltage is equal to the ratio of this resistor, 1 over CS, to the total resistance, which is 1 over CS plus R. If we multiply the top and bottom by CS, to clear the fraction, we end up with y over u equals 1 over RCS plus 1. We got the right answer. Now let's see the advantage of using Laplace transforms to analyze capacitors. I'm going to draw a slightly more complicated RC circuit, and then we'll use our newfound tools to analyze it. Okay, so here I have the input voltage U again, a resistor R connected in series with the resistor R and capacitor C that are connected in parallel. Now, because we're going to use Laplace transforms, instead of writing this as C, we'll write it as 1 over C times S. And then we can just use the tools that we normally use to analyze resistors to analyze a circuit with a capacitor in it. So we're going to take this block, the R and the 1 over CS that are in parallel, and combine them to create an effective resistor. We know the formula for equivalent resistance, or R effective, for two resistors in parallel is R1 times R2 over R1 plus R2. Let's apply that formula with R1 being R and R2 being 1 over CS. And what we get is R over CS over R. So this circuit can be analyzed as if it were and this resistance here is this equation here, R over RCS plus 1. And now this is the output voltage Y. And this is the input voltage U. So again, we can do algebra to analyze these two circuits in parallel. We don't have to write differential equations. We just use all the all the formulas that are already familiar to us. Okay, now this is a voltage divider again. We can use the voltage divider equation. So Y over U is this resistance here, R over RCS plus 1, divided by the total resistance, which is the sum of those two. So I have R plus R over R. Once again, I clear the compound fraction. I get Y over U equals R and finally, I'm going to divide the top and bottom by R. So that will cancel out this R, and this R. And I end up with the transfer function Y over U is 1 over RCS plus 2. Okay, I want to spend just a couple of minutes talking about the consequences of the algebra we did on the last problem to understand this circuit. So I want to compare it to a standard first order filter, low pass filter. What kind of time response do we expect from this transfer function? A little bit of sanity check that we got the right answer. So let's consider the case where we put a step input into both these filters. So I'm going to draw the voltage U, start at 0 here, and U goes over, let's do a unit step. So here's U. I put a voltage of 1, a step change of 1 volt. We know how the first order filter responds, the standard first order filter responds. Initially, the voltage starts to increase rapidly. As the capacitor begins to charge, the voltage drop across the resistor is lower, so the current flows more slowly through the resistor, and the capacitor gains charge less quickly. So this rate of increase of voltage begins to slow, and eventually the capacitor does reach steady state where it's equal to the input voltage. And we know that the time it takes to go about 63% of the steady value, so something like this time here is the time constant, which in this case is just RC. Now, what happens in the case of the modified circuit? Well, initially, when I put the step input in, there's no charge on the capacitor. There's a voltage here. Current begins to flow through the resistor, but because there's no voltage at the output, there's nothing to push that current through this resistor. So all of the current initially going through the resistor has to go through the capacitor, and initially this circuit should behave exactly like this one, because this resistor isn't taking any current, so it has no effect initially. So this graph will begin along the same trajectory as the regular RC circuit. But now, as voltage begins to accumulate here, some of the current that used to be flowing onto the capacitor is leaking through this resistor. So the capacitor will gain charge more slowly than the original circuit. So it will start to slow down like this. And as this capacitor gets more and more charged, more and more of the current goes through this resistor. When the capacitor is equal to a half of the input voltage, then the voltage drop across these two resistors is equal, and all of the current is going through the resistor. So we know we're going to end up at a steady state of a half. And that will happen like this. And we'll get to 2/3 of that value in half of the time we did here, because we can rewrite this equation as a half over RC over 2S plus 1. This is the steady gain of a half, and this is the time constant for the second circuit. So here we have tau 2 is RC over 2. So that's the intuition that goes behind the math we did using Laplace transforms.